Hello everyone, welcome back to my channel InfoSec Lab. Today we'll continue our series on TryHackMe web app pen testing, and the topic is going to be HTTP2 request smuggling. The binary protocol is specifically designed to be hack-proof and kill request smuggling forever. Its precise boundaries were supposed to make up the protocol's message format impossible for machines to misinterpret. However, here's the reality. In modern environments that downgrade traffic to older protocols, HTTP2 can actually make it easier to smuggle malicious requests than ever before. If you want to protect your infrastructure, you have to stop trusting the protocol's reputation and start learning how to focus on H2CL to hijack user sessions and bypass every front-end restrictions in your way. Now, don't worry if you don't know what these mean. As we go through the room, you'll learn what these are. The learning objectives of the room is to understand the basics of HTTP2, learn how to exploit HTTP request smuggling via the HTTP2 version, and last but not least, we're going to use some tools to detect and exploit this vulnerability. Now, without further ado, let's get started. Let's talk about HTTP2. The second version of the HTTP protocol proposes several changes over the original HTTP specifications. The new protocol intends to overcome the problems inherent to HTTP 1.1 by changing the message format and how the client and server communicate. One of the significant differences is that HTTP2 requests and responses use a completely binary protocol, unlike HTTP 1.1, which is humanly readable. This is a massive improvement over the older version because it allows any binary information to be sent in a way that is easier for machines to parse without making mistakes. While HTTP2 binary format is difficult for humans, we will use a simplified representations of requests throughout the room. Here's a visual representation of HTTP2 requests compared with an HTTP 1.1 request. As you can see right here, on the left side is HTTP2 and on the right side is equivalent HTTP 1.1. Let's break down an HTTP2 request. Pseudo headers. HTTP2 defines some headers that start with a column. Those headers are the minimum required for a valid HTTP2 request. In our image, we can see that the method, path, scheme, and authorities are pseudo headers. After the pseudo headers, we have regular headers like user agent and content length. Note that HTTP2 uses lowercase for header names. You can see right here, user agent is lowercase, content length is lowercase, but in HTTP 1.1, user agent is not lowercase at all. The same with the content length. Request body, like HTTP 1.1, this contains any additional information sent with the request, like post parameters, uploaded files, and other data. So this is straightforward. Another important change in the structure of a request that may not be obvious is that HTTP2 establishes precise boundary for each part of the request response. Instead of depending on specific characters like the \r, \n to separate different headers, or the column to separate the header name from the header value like HTTP1, HTTP2 adds field to track size of each part of the request or response. Request smuggling and HTTP2. One of the main reasons HTTP request smuggling is possible in HTTP 1 scenarios is the existence of several ways to define the size of a request body. This ambiguity in the protocol leads to different proxies having their own interpretations of where a request ends and the next one begins, ultimately ending in request smuggling scenarios. The second version of the HTTP protocol was built to improve on many of the characteristics of the first versions. The one we most notably care about in the context of HTTP request smuggling is the clear definitions of sizes for each component of an HTTP request. To avoid the ambiguities in HTTP1, HTTP2 prefixes each request component with a field that contains its size. For example, each header is prefixed with its size, so parsers know precisely how much information to expect. To understand this better, let's take a look at the capture request in Y-chart. Over here, we have the pseudo header method with the value get. Within this one, we have the name length, which is the length of this method we have 7. 1, 2, 3, 4, 5, 6, 7. And the name of the pseudo header is method. Similarly, we have the length of the value, which is 3, and the value is get. In the image, the request body also includes a length indicator, rendering headers like the content length and the transfer encoding chunk meaningless in pure HTTP2 environments. Even though content length headers aren't directly used by HTTP2, modern browsers will still include them. For a specific scenario where HTTP downgrades may occur. This is very important for our specific scenario, and we will discuss it in more detail in the following task. With such clear boundaries for each part of the request, one would expect request smuggling to be impossible, and to a certain extent, it is in the implementations that rely solely on the HTTP2. However, as with many new protocol versions, not all devices can be upgraded to it directly. This results in implementations of load balancers or reverse proxies that support HTTP2, serving content from server farms that still use HTTP1. Answer the question. Which version of the HTTP protocol uses \r\n to separate the headers in the request? Is HTTP 1.1. Which version of the HTTP protocol uses a binary format and clearly defines boundaries for elements in request responses? HTTP2. HTTP2 Desync. Before we talk about HTTP Desync, let's talk about HTTP2 downgrading. When a reverse proxy serves content to the end user with the HTTP2 in the front end, but requests its from backend servers by using the HTTP 1.1, we talk about HTTP2 downgrading. So in simple language, the client side uses HTTP2, whereas the server side uses HTTP 1.1. Instead of dealing the This type of implementation is still common nowadays, making it possible to reintroduce HTTP request smuggling in the context of HTTP2, but only where downgrades to HTTP 1.1 occur. Instead of dealing directly with HTTP2, we send HTTP2 requests in the frontend connection to influence the corresponding HTTP 1.1 request generated in the backend connection so that it causes an HTTP desync condition. Ideally, the proxy should safely convert a single HTTP2 request to a single HTTP 1.1 equivalent. This is only sometimes true in practice. Each proxy implementation may handle the conversion slightly differently, making introducing to a malicious HTTP 1.1 request in the backend connection possible, leading to any of the typical cases of HTTP desync. The expected behavior. Before getting into the request smuggling, let's understand how a request would be translated from HTTP 2 to HTTP 1.1. Let's take a look at the following post request. The process is straightforward. The headers and the body from the HTTP 2 request are directly passed into the HTTP 1.1 request. Notice that the HTTP 2 request includes a content length header. Remember, HTTP 2 doesn't use such header, but HTTP 1.1 requires one to delimit the request body correctly. So any decent browser will still include the content length in HTTP 2 request to preemptively deal with HTTP. In the case of the proxies we'll be using, the host header is added after all other headers, based on the content of the authoritative pseudo header. Other proxy implementations may have other host header appear before the rest of the custom headers. H2CL. As mentioned before, the content length header has no meaning for HTTP2, since the length of the request body is specified unambiguously. But nothing stops us from adding a content length header to an HTTP2 request. If HTTP downgrades occur, The proxy will pass the added content length header from the HTTP2 to the HTTP 1.1 connection, enabling a desync. To better understand this, consider what would happen with the following HTTP2 request. The proxy receives the HTTP2 request from the frontend connection. When translated into the HTTP 1.1, it simply passes the content length header to the backend connection. When the backend server reads the request, it acknowledges the injected content length as valid. Since the injected content length is now, in our example, is 0, the backend is tricked into believing this is a post request without a body. Whatever comes after the headers, the original body of the HTTP2 request, will be interpreted as the part of a new request. Since the word hello is not a complete HTTP 1.1 request, the backend server will wait until more data arrives to complete it. So we can see right here, method is post, the path is the home page, and the scheme is HTTPS. Authority is going to be the TryHackMe.com, which is translated into the host header right here, TryHackMe.com. And user agent is the same. The content length is also passed into the HTTP 1.1. So in the front end, this is a completely one request. But in the back end, because of this content length of size 0, it is split into two separate requests. And the first request ends here. The hello part will become the new request. And this is an incomplete request. The backend connection is now desynced. If another user sends a request, it will be concatenated to the hello value lingering in the backend connection. For example, another user makes a request right after. This is what will happen. This is the second HTTP2 request, and it's a GET request. When translated into HTTP 1.1, it becomes something like this. Because we had the hello value lingering before, it gets concatenated here. This effectively alters the request of the victim user, which can be abused by the attacker in many ways. So, as you can see right here, this is a complete HTTP 1.1 request. Even though we don't get the correct format or the data and the request is malformed, it's still a complete one. We can also add a transfer encoding junk header to the front-end HTTP2 request, and the proxy might also pass it to the backend HTTP 1.1 connection untouched. If the backend web server prioritizes this header to determine the request body size, we can desync the backend connection once again. And the logic is the same. We have this header right here doing nothing, and here is the body of the HTTP2 request. When translated into 1.1, this is where the request ends, and whatever after this one will become the part of the second request, which is right here. The effect will be the same. The first request is now junked at request. Like the H2CL, this request is incomplete. Whatever comes after will be concatenated to this one. CRLF Injection. CR stands for character return, and LF stands for the line feed. These are the special characters that are used in HTTP connections a lot. Remember earlier we talked about the \R and \N. These are the two special characters that we talk about. CRLF is simply the sequence of both of these characters, one after another, and is used in HTTP 1.1 as a delimiter between headers. We also separate the headers from the body by using the double CRLF. Since HTTP2 packets can handle binary information, inserting any special character in any request field is possible. This poses a problem when translating requests into HTTP 1.1, as some characters like the CRLF represent delimiters between headers. If we can inject the CRLF into an HTTP2 header, it might get translated by the proxy into HTTP 1.1 directly, which will be interpreted as the header separator, thus allowing us to smuggle requests. To understand this, look at what will happen if we send the following HTTP2 request. we have a custom header right here with full, and the value is bar. Within this value, notice that we injected the content length header and another part of the GET request. When translated into the HTTP 1.1 version, it would become something like this. All the way up to here is similar to what we've talked about. Over here we have the full, which is the custom, and we have the bar. To understand this, look at what will happen if we send a following HTTP2 request. The resulting HTTP 1.1 request now has an ID header. Note that we aren't limited to injecting headers, so we can also smuggle entire requests in this way. CRLF injection is not restricted to HTTP2 headers only. Any place where you can send a CRLF can potentially end up in the HTTP 1.1 request could potentially achieve the same results. Note that each proxy will try to sanitize the request differently, so your mileage may vary depending on your target. Practical example. In this example, we will exploit H2C vulnerability in an old version of Varnish proxy. In this lab, the proxy uses a single backend connection to handle the incoming requests of all users so that we can use the H2C vulnerability to interfere with other users' requests. The applications can be accessed through the following URL and simulates an extremely simple social network. In this case, you can see your own post and like and dislike them. We will use the H2C vulnerability to force other users to like our post. First, let's analyze how the application works. By simple inspection, we can find out two important things. The application stores a session ID cookie in your browser with your assigned username to track your identity. To like a post, GET request is sent to the following endpoint, post/like/the post ID, where the post ID is the ID of the post we want to like. We can safely guess that the application will identify which user likes the post from the session ID cookie. To force other users to like the post, we can send the following post request. Again, this proxy uses HTTP2, and then in the backend server, it will be translated into HTTP 1.1. This is what our request looks like. Why are we using the post request? Because we want to send a request with a body. Since we set the content length to 0, the backend will think the post request has no body, and whatever comes next will be interpreted as a separate request. We are smuggling an incomplete GET request to the following endpoints. This request corresponds to giving a like to our post. Since the request is unfinished, the backend server will wait for more data to come in the backend connection to complete it. If another user were to send a request to the website right away after, their request would be appended to our incomplete request. As a result, the backend server would receive the request like the following. So first, this is how our request is translated into two separate HTTP 1.1 requests. Over here, the F value is lingering in the second request, waiting for the next incoming request. Another user comes in, it becomes like something like this. We have the GET request. And because this one is concatenated with the F value, the whole thing right here becomes the value of this X header. And whatever comes next, it will become a regular HTTP 1.1 request. We have the host header, we have the user agent, we have the cookie session ID, which is the victim session ID cookies. This looks like a regular GET request that like our post. As a result, we make the victim automatically like our post without his or her knowledge. Okay, so let's try that. Copy this one. Let's see with like and dislike. Like, okay. This is a simple application, there's nothing else. Okay, make sure the intercept is on and we turn on Burp Suite over here. And let's send the request one more time. We have to accept the risk, continue. Let's do it again. Now we get a request. Send it to repeater. Remember, we need to use the post request, so this one has to be post. And we get to this one, it doesn't really matter. Secondly, we have to add the content length, which is 0. Also, we add another one, which is get request to this endpoint. We have to HTTP 1.1. There's two things to pay attention to. First, you have to disable the settings. Otherwise, when you send a request, Burp Suite will automatically update the content length. So you have to turn it off. Second, make sure that there's no extra spaces after this F, because our purpose is to connect request into this F. If we have some extra space, it doesn't work. Alright, everything looks good. Let's try it. Look at what we get. TryHackMe, my name is Flag. HTTP2 request tunneling. Request tunneling versus desync. So far, the attack vectors we have looked at depend on the backend server to reduce a single HTTP connection to serve on users. In certain proxy implementations, each user will get its own backend connections to separate the request from others. Wherever this happens, an attacker won't be able to influence the requests of other users. At first sight, it will appear that we can't do much if confined to our own connection. But we can still smuggle requests through the frontend proxy and achieve some results. Since we can only smuggle requests to our connection, this scenario is often called request tunneling. In the following 3 tasks, we will use an older version of HAProxy, vulnerable to CVE 2019 19193.30 as our frontend proxy. This version allows request smuggling by using a CRLF injection technique. The vulnerable backend application will be accessible through the proxies at the URL port 8100. Request tunneling. Leaking internal headers. The simplest way to abuse request tunneling is to get some information on how the backend requests look. In some scenario, front-end proxies may add headers to the request before sending to the backend. If we want to smuggle a specific request to the backend, we may need to add such headers for a request to go through. To leak such headers, we can abuse any functionality in the backend application that reflects a parameter from the request into the response. In our case, the application reflects whatever data is sent to hello through the queue post parameter. Here's how the request looks like. When a user input a keyword to search, this is what an HTTP2 looks like. Everything is the same. The content length is 14. Let's double check. 2, 4, 6, 8, 10, 12, and 14. So the content length is 14 in this case. Notice that the existence of the content length header despite being ignored by the HTTP2. Most browsers will add this header to all HTTP2 requests so that the backend will still receive a valid content length header if an HTTP downgrade occurs. In the backend, the request will be converted into HTTP 1.1. This particular proxy will insert the host header after the header sent by the client. If needed, the proxy could also add additional headers, represented as the X internal in the image. The final backend request would look something like this. So this is the front-end headers. After being translated into the HTTP 1.1, the host header is added. We have some internal headers appended to the host header. And then after that is the query right here. We will take advantage of the vulnerability in the HAProxy that allows us to inject CRLFs via the headers to leak the backend headers successfully. We will add a custom full header and send our attack payload through it. This is what the full header looks like, with bar, content length, host, post, everything. And then when translated into the HTTP 1.1, it becomes something like this. The first part is pretty straightforward. You have the full header with a value bar, and then we have a content length of size 0. And the host header is right here. The reason we have the host right here is because without this one, the first HTTP 1.1 request will become invalid. It has to have the host header. That is why. And then because the content length is 0, this is a post body. So this is the end of the first request. Whatever next is the part of the second request, which is this one, the post hello and the HTTP 1.1. Now for the second post request, it's a little bit tricky. Remember earlier, we talked about when translating an HTTP 2 request to HTTP 1.1 request, for these specific proxies that we are using, the host header will be added after any other headers. So in this case, we see the host header is added right here after the full header right here. But because of the malicious values in the full values, these host headers become part of the search query that we input right here. So instead of being a header, this becomes part of the search results that will be presented on the application. That is why the host appears at the end of this one. Alright, so let's try that. So first, we're going to turn off the Burp Suite. Disable it. And the application is on port 8100. Yes. Set the request. Let's pass it to the proxies. Yes, resend. Here in backend, forward. One more time. Send it to repeater. Okay, so let's try that. So first thing first, always make sure the request is HTTP 2 over here. Sometimes they may be using HTTP 1.1, so always make sure that it uses HTTP 2. Second thing is to disable this one. Make sure that you do it first, always. Otherwise, it just automatically updates your content length. Now next, we look for the content length, which is not right here. So, which is not here, so we're going to do it content length. Which is 0. And we have to delete this one. Now, the next step is to create our custom header. Now usually we can add the custom header from here, But remember, HTTP2 uses binary format, so we can't, and we also inject the CRLF. We can't really do it here. We have to do it from the right pane right here. Click this one. We see a list of the headers, and click this plus icon right here. Full is the name of the header. Name is going to be bar. Over here, to inject the CRLF, hold the shift and then press enter. You're going to see these two characters like this. And we have to put the host name again. Okay, so what else do we need? We also need the content length of size 0. Okay, so I guess we delete this one. Over here we have content length size 0. We have the host. Okay, now we have this part of the request, which is the post hello. HTTP 1.1. Inject the host one more time. No, not this one. We have the host, we have the content type, and the content length, and the body of request. Okay, content. This application. X URL encoded. Content type is equal, let's make it 5, and the search parameter is equal this one. Right here, everything's correct. Do we have the host? Yes, we have the host header. Okay, over here we also have to make sure that content length is 0, which is right here. We add it. Now, the way we know that we have successfully added the header is over here, where the HTTP2 request is kettle. It contains headers that cannot be fully represented using HTTP1. That's because of the CRLF. So this is expected. What's next? We send a request once, twice. Okay, so we have a bad request. Not sure what I did wrong here. So let's try again one more time. Forward. No, sorry, my bad. Resend it. Repeater. Over here we have the hello post request. First, mark the content length to 0. Second, disable these settings and make sure that it uses HTTP2, so everything's correct. We delete the body and we add a new custom header, which is full. Values is bar. We've got the host name, which is this one. We have the post hello HTTP 1.1. The content length this time is whatever it is, the host, the content type, application. Okay. Same thing, host right here. Content 500. Content type application. Just want to make sure there's no typo. X key and the Q and the search. Okay, this one disable HTTP 2. When the request is ready, you can press the send button as usual to send it. Remember that our HTTP 2 request will be split into two backend requests. So the first time you send it, it will only obtain the response for the first request, which is empty. To get the value of the hidden internal headers, you will need to send the same request twice in quick succession. If all goes well, the website should reflect the internal headers of your second request. So 1, 2. There we go. We get the internal header right here. Bypassing frontend restrictions. In some scenarios, you will find that the frontend proxies enforces restrictions on what resources can be accessed on the backend website. For example, imagine your website has an admin panel at the /admin, but you don't want it accessible to everyone on the internet. As a simple solution, you could enforce restrictions in the frontend proxy to disallow any attempt to access the /admin without requiring any changes in the backend server itself. So let's try to access this one, and we'll get a message telling us the request has been denied. A request tunneling vulnerability would allow us to smuggle requests to the backend without the frontend proxy noticing, effectively bypassing frontend security controls. Considering the following request, we also have the post request. Same concept, we inject the custom full header with the malicious value. And within this value, we embedded a new get request right here. We're still using the post request. The reason is there's a fundamental difference on how get and post requests are treated as a proxy. If a proxy implements a caching, get requests may be served from the proxy's cache, so nothing will be forwarded to the backend server and the attack may fail. A post request, on the other hand, is normally not served from cache, so it is guaranteed that it will be forwarded to backend. When the frontend sees this HTTP 2 request, it will interpret it as being directed to the hello, which is allowed the proxy's ACL in the backend. However, the HTTP 2 request gets split into two HTTP 1.1 requests, where the second one points to the admin. Notice the second request is purposely unfinished, so we will need to send the request twice to trigger the response corresponding to /admin. Another way to understand the attack would be to say that we are using an allowed resource, in this case the hello, to smuggle a request to a forbidden resource, in this case /admin. From the point of view of the proxy, only a request for the hello was made, so no violations to the ACL were made. It is important to note that the resource we request via the HTTP2 must be allowed by the ACL for this attack to work. We are effectively smuggling an invalid request over a valid one. The same method can be sometimes used to smuggle requests past the web application firewalls. Okay, let's try that. Now, intercepts up, intercepts on. We also have the following request, resend it. Let's go to the backend right here. Forward that to a repeater. Again, we're going to use the same. First, delete the body. Second, disable this update content length. Make sure it's HTTP2, and we set the content length to 0. Right here, concept is the same. And over here, we also add the custom header, which is full bar. We add a host, which is this one. Doing the content length? No, we don't need a content length. Now get admin http 1.1 x. We also have the host header, and then we have x. Let's double check. We actually don't need this one. Okay, again, this one, make sure there's no extra space after the F. Add the request schedule, which is correct. Now send the request twice. Boom. We got a flag. HTTP2 request tunneling, the web cache poisoning. Even if we can't influence other users' connections directly, we may be able to use request tunneling to poison server-side caching mechanisms, affecting users indirectly. This kind of attack has high severity as it impacts all users visiting the website, as long as the cache content lasts. Given the right conditions, the poison cache content can have anything the attacker wants, including JavaScript payloads. This can be used to issue malicious redirects or even steal user sessions. Note, extreme care needs to be taken when testing web cache poisonings in real-world production systems, as they may affect the availability of the website if not conducted properly. Understanding the scenario, for this task, we are still using the HAProxy. The HAProxy instance is configured to cache content for 30 seconds, so we should be able to perform the attack. Also, if something gets cached wrongly while you were doing the test, waiting for 30 seconds will clear up the cache so you can start from scratch again. Before diving into the details, let's lay out the plan. To achieve the cache poisoning, what we want is to make a request to proxy on a page 1 and somehow force the backend server to respond with the content of the page 2. If this were to happen, the proxy will wrongly associate the URL of page 1 with the cache content of page 2. The trick we are using will allow you to poison the cache, but only with the content of other pages on the same website. This means the attacker wouldn't be able to pick arbitrary content for the cache poisoning. Luckily for us, there's some ways to overcome this limitation. If the website has an upload functionality, if we find a part of the website that reflects the content of a request parameter, we can abuse articles or any equivalent content to the website. Under certain circumstances, open redirects can also be abused, but we won't cover this case during the room. In any of these cases, the attacker may add arbitrary content to the website, which can be cached by proxies and associated with the URL. In the case of our application, we have an upload functionality at the disposal of the following URL /upload. We can use this to upload any payload we want to catch later. Executing plan. Our goal in this task is to be stealing the cookie from any user visiting the website. The lab already simulates a victim user, so the flag of the task will be that user's cookies. One option we could use would be pausing the cache from the home page directly, but we want to be a bit more silent about things. By quick inspection, we can notice that the home directory executes the show text JavaScript function when the page's body loads, which is defined in the static text.js right here. Let's try to version the cache version of the static text.js to include a JavaScript payload to steal the user cookies. Since we need a JavaScript payload on the website before the cache versioning, let's start by uploading the following payload in the file name myjs.js. So first we're going to create this one. myjs.js. Paste it. Do we need to make any notification? Yes, we do. So over here, we have to modify with our attack box. Over here, we have to replace with our IP address. 10. This is a simple payload that will forward the victim's cookies back to our web server controlled by the attacker. Be sure to replace the IP address with the IP address of your attack box, which I've already done. The only special things about this payload is that it forwards the cookie via the HTTPS. We need to use HTTPS since HTTP2 runs over HTTPS by default. If a script in an HTTPS website tries to load a resource using plain HTTP, most browsers will block the action for security reasons. This means your standard Python HTTP server won't actually be able to receive the cookies, but more on that later. After uploading our payload, the website will let us know that the file has been uploaded to the static /upload/myjs.js. We now need to poison the cache so that it serves our payload wherever the text.js is requested. To do so, we will use the following request. As usual, we're going to have a custom header which is full, and its value is going to be our malicious payload right here. So when translated into HTTP 1.1, it will become separate request. Here, we're using the CRLF Injection vulnerability in HAProxy to perform a request splitting attack in the backend. The first backend request will contain the text.js. The second request will be for the myjs.js. The proxy should expect a single response to its request, but it's getting two instead. The proxy will take the first response and serve it to the user, and keep the second response queue in the backend connection. Also, if we notice, we have the pragma no cache header in our request to force the proxy to bypass any cache content and send the request to the backend server. Doing so allows us to send several requests until our payload is correctly triggered without waiting for the cache to time out. If we now send an additional request to the text.js, we will get the queued response with the contents of myjs.js. Beyond the fact that we are receiving the wrong content for our new request, the cache will wrongly associate the contents of the queue response with the new URL we are requesting. Any other users that request the text.js afterwards will receive the contents of myjs.js served from the poison cache instead. This will last until the cache content expires, which is about 30 seconds. Now, if your attack works, You should now be able to curl the request static text.js and should get the contents of a payload instead. The following command will allow you to check if the attack worked. To curl over here. Also, we will use our actual browser to check if the attack worked. Browsers also have local caching. It may alter what you get from a URL, as it may be taken directly from your local cache instead of being requested to the proxies or the web server. Now let's talk about setting up an HTTPS server for our payload. At this point, if the victim user navigates to the home page, the cookies will be sent to our attack box on port 8002 via the HTTPS. We need to set up a simple web server that implements HTTPS to be able to read the received cookie. There are many ways to set up such a server. We will use Python. Before running the HTTPS web server, we will need to create an SSL certificate. And the key next, we'll create a file named https.py with the code responsible for running the HTTPS web server. The code is straightforward and let you specify the port to use, which is 8002. The code also points to the SSL certificate that we previously generated. Copy this one. Let's double check. Right here, everything's correct. Port 8002. Now, our script is ready. We can run it by the following command. You won't get any output initially, but as soon as the victim navigates to a web server, logs will start to appear. Okay, so we're going to listening on our port right here. You can see right here, this is our malicious JavaScript payload. Now, the next step is we have to poison the cache from the server. Let's do it. So first, we turn on our Burp Suite and we send a request to the home page. Over here, send it to repeater, and we have to make some modification. Okay, first we have to get static text.js, and over here we have to add pragma, no catch, and we add a new, and we're going to add a new header, full bar static uploads my.js http 1.1. Now we save the payload. The request is kettle, which is expected. Now let's send it once we have nothing, send it another one, and then we get the following response right here. And as you can see right here on our Python listener, we received the user's cookie, which is this one, nominal cookie. So what does it mean? Because the content of text.js has been poisoned, now the application is serving the content of our malicious payload my.js.js, which steals the user's cookie and send it to our Python listeners. Okay, so we have successfully exploited this vulnerability. H2C Smuggling. Web servers can offer the client many HTTP protocol versions in a single port. This is useful because you can't guarantee that users will always have HTTP2 compliant browser. In this way, the server can offer the client both HTTP 1.1 and HTTP2, and the client can select the version they want to use. This process is known as negotiation and is handled entirely by your browser. The original HTTP2 specifications define two ways to negotiate HTTP2, depending on whether the communications were encrypted or not. The two methods use the following two protocols identifier. H2, protocol used when running HTTP2 over protocol used when running HTTP2 over a TLS encrypted channel. It relies on the application layer protocol negotiations mechanism of TLS to offer HTTP2. H2C, HTTP2 over clear text channels. This will be used when encryption is not available. Since application layer protocol negotiation is a feature of TLS, you can use it in clear text channels. In this case, the client sends an initial HTTP 1.1 request with a couple of added headers to request an upgrade to HTTP2. If the server acknowledges the additional headers, the connection is upgraded to HTTP2. The H2 protocol is the usual way to implement HTTP2 since it is considered more secure. In fact, the H2C specification is now regarded as obsolete to the point where most modern browsers won't even support it. Many server implementations, however, still support H2C for compatibility reasons, enabling a different way to smuggle requests. H2C upgrades. When negotiating a clear text HTTP2 connection, the client will send a regular HTTP 1.1 request with the upgrade H2C header to let the server know it supports H2C. The request must also include additional HTTP2 settings headers with some negotiations parameters we won't discuss in detail. A compliant server will accept the upgrade with a 101 switching protocol's response. From that point, the connection switches to HTTP2. Tunneling requests via the H2C smuggling. When an HTTP 1.1 connection upgrade is attempted via some reverse proxies, they will directly forward the upgrade headers to the backend server instead of handling it themselves. The backend server will perform the upgrade and manage communications in the new protocol afterwards. The proxy will tunnel any further communications between the client and the server, but won't check the content anymore. Since the connections of HTTP2 are persistent by default, you should be able to send all the HTTP2 requests, which will grow directly into the backend server through the HTTP2 tunnel. This technique is known as H2C smuggling. Note that for H2C smuggling to work, the proxy must forward the H2C upgrade to the backend. Some proxies are aware of H2C and could try to handle the connection upgrade themselves. In those cases, we end up with a front-end connection upgraded to HTTP2 instead of a direct tunnel back to the backend, which wouldn't be much of use. When facing an H2C aware proxy, there's still a chance to get H2C smuggling to work under a specific scenario. If the front-end proxy supports 1.1 over the TLS, we can try performing the H2C upgrade over the TLS channel. This is an unusual request since H2C is defined to work under clear text channels only. The proxy might just forward the upgrade headers instead of handling the upgrade directly, as it wouldn't make sense to have H2C over unencrypted channel according to the specification. Note that H2C smuggling only allows for request tunneling. Poisoning other users' connections won't be possible, but as we already shown, this could still be abused to bypass restrictions on the front end and even attempting cache poisoning. Now let's talk about bypassing front-end restrictions with the H2C smuggle. In this scenario, we're attacking the application's expo on port 8200. The application is served through a HAProxy instance with default configurations. The application exposes to endpoint, the homepage, and the private folder. The private folder endpoint is not allowed through the proxy. You can try accessing that, and you should get a 403 forbidden response. We'll be using H2C smuggling to get the contents of the private through the proxy. We will use the H2C smuggling tool provided by Bishop Fox. The tool will perform the full attack for us, since doing it manually will be somewhat complicated. The following command will first attempt an H2C upgrade while requesting the homepage. Since that resource is allowed by the proxy, the connection will upgrade successfully to HTTP2. The HTTP2 tunnel would then be used to request the private directory by passing the front-end restriction. So I guess we'll just copy and paste this one. Let's see. Okay, so let's first download this one. Now we can copy and paste the command, which is this one. No. Copy, paste. Oh, we have to run the do we need to, so we have to install the, okay, so we're gonna have to install this one. Okay, we run it and we get a flag right here. Okay, because of the complexity of this vulnerability, we're not going to go deep into this. So that's it for the room today. Thank you very much for watching, and I hope you enjoy this room. I know there's a lot of information for this room, so it's okay to get confused. It's okay to get overwhelmed by the information. If you have any questions during the room, feel free to put a comment below. I'll be happy to help. Thank you very much, and I'll see you next time. Bye bye.